In this lecture, I will continue with you the two functions in the binary search tree found in the theory section. If you check the slides, Dr. Abdul Hafiz gave to you, or I think he will upload it soon. In the binary search tree, you started with the operations in the BST like search. There was also insertion, deletion. So insertion and deletion, I will try to explain to you today.
Okay.
But by doing so, the lecture will be complete for the BST. And then next lecture will be about something called hash tables for next week, and the same thing for the lab.
Okay, sir.
Okay. So let's start with the insertion. I will try to explain the theoretical part, then move to the practical part. Insertion means you are trying to add a new node to your tree, and you need to preserve the property of the binary search tree. That means you already know that binary search tree has a specific way of building it. I mean, like
Yes.
The left branch is smaller than the right branch, and so on. So when you try to insert something, you need to find a way to insert the node in the right place. And that's what you read, that the binary search tree property continues to hold. That means continue to be true. So the most important thing is to insert the node in the right place, not to insert the node any place in the tree. If we express this by a pseudocode, and again, pseudocode is just writing the Euro program with the normal speaking language, without having like language specific keywords. We can express by a function called tree insert. Takes the tree or the root of the tree as a pointer, and z as the pointer you want to add to the tree. Inside this function, we have two variables. And by the way, this function is written in the reference. The reference is the Introduction to Algorithms by MIT Press. It's one of the references in this course. The pseudocode of this functionality of BST is written without using recursive style. So we will explain it without recursive style, but we will solve the practical example using recursive style. So you can understand both, the one without recursive and the one with recursive. So again, T is the tree and Z is the node you are trying to insert. You have two variables, Y and X. Y initialized with null and X initialized with the first of all with the root.
Roots. Okay.
Yeah. And then you iterate in this while from line number 3 to line number 7, and try to change the value of X and Y. First of all, we started Y with null, but first of all, we assign the X pointer to Y, and X start from the root. So currently Y is equal to the root and X equal to the root. Now we check if the key of the node we are trying to insert is smaller than the current value of X. I mean we are trying to traverse using in this tree. If it's smaller, that means we should go to the left. To the left, yeah, and currently it's in the root. We are pointing to the root in the X, so we go to the left of the root, or it will be smaller, so we go to the right.
Yes, exactly.
Yeah. So we stay iterating until we reach to x equal to null. When we reach to x equal to null, because each iteration we update the value of x, this this local variable inside the function, we update the value of x with x left or x right, depending on the value of z key, or key of z, the new node we want to insert. So we reach to the end of this while loop when x equal to null. That means we reach to the leaf. That means we reach to the final node in a tree. So there is this is the area that we should insert the node to it, because let's draw like simple, or let's see an example. 1 second.
Okay. Sir,
Yeah.
I won't use my microphone unnecessarily because there's too much noise. Sorry, I told them, can we make it like, can we sound off? But they said the whole system is part of one system, so they can't do that. Sorry.
Yeah, no worries, no worries. Is it in the university?
No, it's near to my house.
Ah, okay, yeah.
Yes, I come here because there's no internet connection in my house right now.
Yeah, sure. I wanted to show you an example, so I will use this website. I already mentioned it to you. So we have now like a simple tree. It's it. We have like simple binary tree like this one, and let's say we want to add a new node equal to, let's say, 10. So if we want to solve it by like imagination, we will say that 10 is smaller than 72. So for sure we will not go to the right, we will go to left. We now check the 55. It's bigger than 10, so we will not go to the left. We will go to the sorry, we will not go to the right. We go to the left.
Yes, because of
21 is also bigger, so we will not go to the right. We can now insert 10 here. Let me check just 1 second the algorithm, if not mistaken. Is equal to null. Are we going? Yeah, it will not go to the right because it's smaller. So it will go. It will point to the left of this node, the 21, which is null. So it will break here and insert the node here. If we are not mistaken somewhere, it should be correct. So let's see now. Let's insert the node 10. The algorithm here is the same of when we saw it. 10. So it was inserted here. Okay.
Yeah. Okay.
Yeah. So the same thing happens here after we finish after we finish searching for the best that we need to add the node to it. We start adding it actually. Just a small note here, it seems here in this reference they have also inside the struct they have parent, so you can you have not you have usually we have left and right pointer to point to the children. Also you can add a new additional pointer called parent, so you can know as a node what is your parent. So each node, let's say node 62, knows in the structure that has a right and left branch, and also this link which is pointing to the parent. So inside this node we have 3 pointers: right, left, and parent. So when we enter 10 as a new node, we will assign 10 dot parent to 21. So this is what's happening here. Z dot p equal to y. Y is pointing actually to the x. So this is a small note just to know from where came this line. Here is just checking if y equal null. That means the tree is empty already. So simply the root will be z, your new node. Else if z key smaller than y dot key. Yeah. Here just like define saying it will be assigned to the y. We said y is the leaf node, and y here is 21. So you decide to add it as left or right. Here for sure will be for left. But let's say you reach to this node or to this node. You have two possibilities to add to left or to right. So here is just you are deciding it. This new node will be added to the right or left depending on comparing
smaller or bigger. Yes.
Yeah, exactly. Comparing the new node key with the leaf node, like here comparing 10 with 21, it's a smaller, so it will be left. So this is basically the pseudocode of this insertion operation of BST. Is it clear?
Yes, it's clear, sir.
Okay.
Thank you.
So here I'm just like giving an example. Let's see how we will add key 13 to this tree. 13 with a dashed line. 13 is bigger than 12. So like if we applied this,
will be right.
Yeah, like if we applied this pseudocode inside this while 13, which is z equal to z, 13 is bigger, so we will go to the right.
Then 18 is bigger, so we go to the left.
Exactly.
Then
we go to the left.
15 is bigger, then we go to the left again.
We go 15. Yeah, bigger. Actually, go to the left, and left is null. So we break, yes. Go out while, and then again start to the assigning the p of z, which is the parent of z. Parent of 13 will be equal to 15, and then decide that this is a left children for 15.
Yes.
Okay.
Okay.
Let's try to write this as an iterative, not iterative, sorry, recursive style. So let's try to write the code here. First of all, as usual, we will define class or struct. Is up to you to use whatever you most comfortable with. We will put public, and we will have end key. We will have a pointer to the left and a pointer to the right.
Pointer to the right.
Yeah. And also we will have like a constructor.
Yes.
We will have two constructors. One default constructor. We name this default constructor when we don't pass any argument. So simply let's say key equal to 0. We'll initialize key equal to 0 and left equal to null. I think here we should use null pointer somehow. ptr. In C++ you have two options, like using null or null ptr. It's same. It's the same actually. Both are the same, but sometimes the version of compiler may not recognize null or may not recognize null pointer. So this is a small note. Right equal to null pointer, like here.
Yes.
And BST here we will assign. We will send a value and let's say key. So now here, do you remember how if we want to distinguish this key from this key, how we can do this? there was a trick.
Yes.
We use this dot key equal to key.
Yes.
Okay. Now we will define an API or a method called insert, and this will return for us PST. It will return for us the pointer to the new created node, and insert will have one or two arguments, a pointer to the root, and let's say T, like for a tree, and the value of key of node we want to insert, int key.
Yes.
So here now we will going to discuss how we will design this as a like recursive style. If you saw from here like this from this simulation, we check each node with the same thing, with the same like procedure. So that means we can solve this problem using recursive. So each node, we simply say each node, we will check if it's if the new key is smaller, we will go to the left. If it's bigger, we go to the right. If we reach to null, we will create a new node. Because when we reach to null, that means we reach to the place where we should add the new
Insert. Yes.
The new node. Yeah. So I will just explain this instead of like normal English with the programming. So if T equal to null or unnull, let's say null BTR, that means you reached. That means this means actually this means two things. The tree is empty or it's you reached
insertion.
Yeah.
Yes.
So empty or reached.
But how we realize the difference between empty or reached position?
There is no need to distinguish the difference, because if it's empty, that means it will not do any iteration. There is no recursive. It's simply from the first time execute. If you remember, we draw in the stack that we have different calls. So if it's empty, it will be called only once. Okay?
Okay.
Yeah. So simply we will say return, and as long as we want the address of the new created node, so we'll simply use new, which is if you remember, it's the dynamic allocation command for C++, new PST, and we pass to it key. So new PST key will create an object from this class and return the address of it. That's why it's PST star.
Okay.
Now we will continue the recursive style. Now to define how the recursive will be grow, because if you remember, we said we have two conditions when we want to design recursive solution. First thing, that we should define an exit point, which means this will break the recursive or the recursion, and you will break the sequence of the calls in the stack. And the second thing, that you should every step go closer to the solution. So we are now in step 2. We need to go closer. So the thing we are going to use to go closer to the solution is make sure that our path will go to the right or to the left. So depending on the value of key, if it's smaller than t dot key, that means what?
Left.
Exactly. Go to left. And now we will say t dot left, and I will explain it very soon. We will say t dot left equal to here we will do the recursion. We will say insert equal to insert t to the left. Sorry, here should be not dot, should be an pointer axis because it's a pointer. So here
Yes.
is to the left of, we will call insert again, but to the left of the, currently we are in the root, so we will go to the left of the root, for example, and also we will pass the key, the same argument here will be passed for the next iteration. Now if I want to explain why we did this, why we did not just wrote something like this, because if you remember, we need to make it connected with the tree, like here when we inserted 10, we should say to 21 to assign the left with the 10, right?
Yes.
So actually how we express this by doing this t to the left, because t will be at some iteration or at some point t will be for here 21, for first time or for first iteration will be 72, but for the last iteration it will be 21. So this actually what this means, like link the last node with the new node, something like this. Now else if, you can say else or else if, it's up to you.
Then right.
Yeah, we go to the right, yes, if key bigger or smaller or equal, sorry, to the t.
Are we going to do the same thing? T pointer to the right, then insert.
Yeah, exactly.
Okay.
Go to right. And say t pointer to right equal, because here again it may be inserted to the right, not to the left, so that's the same thing. Insert t to the right. We pass also key.
Okay, yes.
Okay. Now, finally, do you think that now we are finished? We still have one line of code only.
Insert.
No, now the recursion is finished. We only have two branch. Let's say two ways of recursion. We either go to the right or we go to the left. But here, like, imagine we are now in the root. Okay.
Okay.
We are now in the first call of insert. We are now let's say we have this tree and we are trying to insert 10. So currently we are at 72. So by executing this function or this method, t is not null pointer. It will go to here, and key will be smaller. It's smaller, so we go to left. So if we want to continue calling iteration by iteration, recursive by recursive, first it will be 72, then 54, then 21. Then if you remember, it will break and try to do what? Try to go in reverse to execute what is still in the stack. Do you remember? Like if you remember, where the code here, or not here. Let's say with this example. If you remember, sorry, we have a stack. Okay. We have a stack, and inside stack we store what? I can.
Oh, hello.
Yeah, I'm asking you how we use the stack with the recursive, if you remember.
We are starting from bottom.
No. I mean with the recursive, how we use the stack. Do you remember how we things was done with the stack and recursive? The steps we saw last week.
Yes.
Like first of all, we will call. Let's say this is the start point for us. This is. Let's say we started from here. We have now first call insert. Uh, let's say we passed the root, and we are now want to create node number 10. So we checked the condition which is here. So which is here. It's not null. So we go either to the left. Sorry. We go to the left or to the right. So we know 10 is smaller than the root. So we have a next iteration and say here insert now. Let's say node 54 and 54, and again we want to insert 10. And if you remember, do you remember like here each entry in the stack hold the last line we execute from the instance of the function, right?
Yes, when we go back, we were deleting the.
Exactly, one by one.
Yes,
Yeah.
one more.
So let's just complete the stack and see what will happen. So now insert in 54. It will be now insert 21. Insert 21, and we want to add 10. And last entry here will be insert null. We reach to the null, and we want to insert 10. So insert null. It will this one will create for us. It will create for us the node that we want, because null here, sorry, from the code, it will create for us the new node. It will create for us the address.
Yes.
Okay, but and let's mark this as completed. Now, when we want to complete what's happening inside these functions, N21 stopped at here, at left. So left should be, you are updating the left of a node already exists in your tree. Like 21 is already exist. So you cannot just stop saying, if you executed this code without any additional thing, what will be the value of t left? It will be for this iteration, it will be the new created one. The new created key will be assigned to here, because why? Because again, you broke this, you finished executing this, you return to here, right?
Yes.
So you return to here. Now you are good, but now you finished here. You finished executing here. You finished executing N21. What you will return for N54, like from this code, what you will return? It's not null. You already assigned the left of the left of 21 with 10, what you will assign now the left of 54 from this code? Can you tell me?
The right?
No, because I mean, let me repeat my question again. Now currently in our execution we reached to 21. Okay, let's say
Okay.
remove this. We remove this. We reached to 21. Okay.
Yes.
From the code, first of all, let's memorize this diagram. The state of the stack. We reach to 21. We go to the null, insert null. Here we created, like from the code, when it's null, we create the new node. Okay.
Yes.
Yeah. So my question is, in this stack, when it's null, we created the new node. We went back to the insert n21 to see from where we stopped. We stopped actually in this code and the t to the left insert,
Yes.
right?
Yes.
So the return of this, the return of here, only here, the return of only here, sorry, not like this. The return only here is correct because it will create for you the new node and return the address, and the left of n21 will be pointing to the new node. Now my question is, you are in this iteration, okay, insert n54 from this tree, and you stopped at this line, and now you want to continue. You stopped here and you want to continue. What you will continue?
Yes.
What is left in this function? Is there anything will be executed?
Are we check again conditions?
Okay. Remember, you already checked the conditions.
Yes.
So there is nothing to execute.
Okay.
Okay, so it will return null. It will return 0. So by doing so, if you wrote the code like only this this recursive will be correct, but when you switch from n21 to n54 and you are updating the left of the nodes, it will be assigned to null or to 0 or to whatever, because again, when you exit the execution of a function without a return, it will return for you 0 or null, something like this. So here it's very important to say return what the current key, the current, sorry, node t, return t. So when now if we went back to here, insert null, it will return again, we said it will return the new added node, and now the left of n21, node 21, will be connected correctly. But hereafter, n21 will return its own address. In this case, the left of 54 will be as it is. It will be assigned again with the node of node 21, the address of node 21.
Oh, okay.
Okay, is it now like clear? Why
Yes, we
we
turned it
added
to
here? Why we added this line?
yes.
Okay. So by doing so, we have now completed implementation of this method and this class. We have now int main and 0. Here we want to create est. We have root and t equal null. Sorry, this one should be a pointer, null ptr. Now we will start from like an empty tree. Oh, sorry, here should be. Sorry, like this. This tree is empty currently, so we will insert
Yes.
to t. We'll pass root is equal to null ptr. We will pass root and insert
And key.
sorry, the key,
Key,
yeah,
and
the key.
yes, yes.
Anything, we will insert anything here. So we will now insert one by one, insert the nodes we want for this tree to be built. So we can like say 100, then we insert 10, then we insert 20, 30, whatever.
And the program will sort it automatically, right?
Yeah, so
Will
it will be
sort it.
inserted in the correct place.
Yes.
Yeah. So this is the complete code. This is identical to a code I wrote it yesterday. Like we are building certain tree. Start with like we have the same thing, the same code. We build a tree with this sequence, and just let us execute. First of all, let's imagine how it will be. We have like 100. Let's just imagine the shape of this tree. So if we have like 1 second. Okay. First of all, it will be empty. The 100 will be empty. The 20 is less, so it will be to the left.
Left, yes. And 10 is
10 is
smaller
also
than left.
smaller, so it will be to the left of 20.
But 500 is bigger than
Bigger
100, so we will play
to
right.
the right, exactly. And
then left
30, it will be here.
Eh.
Bigger than 20, so here it will be 30.
Yes.
Okay?
Yes, okay.
And it's just connected like this. So now if we want to check if is it correct, ordered correct, we let's say we will print the left of root. It should be 20. So root left, let me add it here.
We will print the root.
Root, and to the left we will just access the key. I think did I execute this from here or from C++ online compiler? Yeah, from here it's correct. Yeah. Yeah, so it gave me correctly the 20, which is here. I also tried to check the left of the left.
Left of left, and yes, 10. Correct.
And it's 10. So that's how we make sure that this is correct. Now it's your turn for next session to do what? You know, doing this style is not good because you already learned. I mean, if we were in the beginning of this course, it will be hard to ask this. But as long as we explained last session or from 2 sessions the traversing algorithms, the in order, pre-order, Or last session,
Yes.
no, it's last session. If you remember, this traversal algorithm will be go through all the nodes. So I want from you to print the tree using any traversing algorithm you choose. The pre-order, post-order, or in-order, anyone you have it. Just add you have the complete code. You have
All the methods or just one method?
no, just choose any method you want.
Okay, okay.
Just add it to the class. You have here the complete code of the class. You just add for it
Yeah.
a new method.
Are we going to visualize this or just coding?
It's nice to do visualization, but it's not too much easy.
Can
You
I
can
write
search.
can
Yeah.
I write the paper, the tree?
Write on a paper. No, I don't want you to write anything on paper. I want to add as a code. So you
Okay.
simply print. If you remember, do you remember in the when we explained the traversing, we did not have any visualization. We just print the nodes, and from the order of printing, we know that our algorithm, which one is the pre-order or post-order. If you remember, some of them was the first access node or first printed node is the root, and the last one will be the leaf on the most right or most left. Do you remember that?
Yes.
Yeah, so just use print. So from the order of printing, we know the order of our tree.
Yes, I was saying just visualize the tree on the paper, just not coding, just visual.
No need because what you will add if you draw for me a tree
Okay.
on a paper. So it's a program. By the end of the day, it's a program. So no
Okay,
need
so
to do anything on paper.
okay, I
So
got it.
yeah, so just try to do the traversal algorithm and print I mean, try the same example. I mean the same. Oh, I did not provide the example. So try to build any binary tree you want, and then execute the traversal algorithm. You already have the codes from last session. So you just merge the two classes or merge the two codes with each other and print and see, just check that, oh, this is the pre-order, let's say, or in order, and this should the first node should be the root, or last, or should be the last node. So it's up to you. Just print and make sure your work is correct. But again,
Okay.
I just want you to do the code, not the code with the
Okay.
void main, with the int main. I mean, with providing the main,
Yes,
because
yes, I
it's
got it.
you are required to do like use the new method with inside the main. We finished now talking about the insertion. Let's move to the deletion. Do you have any question about insertion?
No, so thank you for explanation.
Okay, thank you. Now deletion is a little bit more complicated than insertion, because insertion you have only like clear case how you will insert a node to a tree. You have like certain steps. There is no too much cases to discuss. But in deletion, you have different cases. Let's say we have this tree here in the up left corner. We have multiple, let's say, options or multiple scenarios or multiple cases of deleting a node. We may delete a leaf. The simplest one will be deleting a leaf. So if you want to delete 20, this is the most simple one. We simply delete the 20 and assign null to the for the pointer of the parent from the left. It will be equal to the null.
Yeah.
Okay, this is the simplest. But what if we want to delete 30 from here? Now we need to bring the child, and put it in the place of 30, and update the link between 50 from instead of pointing to 30, it will be pointing to 40.
Yes.
More harder, let's say we want to delete the root. What we should do?
We do. We do first the deletion, and then we choose the smallest one on the right node, because they have to smallest for the right, because they have to be bigger. Right has to be bigger. So
Exactly.
we choose the smallest right node,
Exactly.
and then we decide the root.
Exactly. This thing you explained called successor. I don't know if you took it with Dr. Abdul Hafiz. There was a slide for successor operation.
Yes,
Yeah. Okay.
I guess.
So whenever you want to delete 50 or any other, let's say, node that has two branches, you need to bring the successor and put it instead of the node you want to delete. So here 50, if we want to give the successor means you go to the right and select the smallest bigger value than 50. So all of the values
Yes,
on the right are bigger than 50, but one of them is the smallest bigger value, which is 60. So we bring 60
yes,
and put it here, and the tree will be like this. 60 will be removed from its place, 50 will be deleted and replaced by 60. So it will be something like this.
yes,
But I want to drag your attention. Some references use something called where here the bread scissors bread scissor. Yeah,
yes,
if I'm spelling correct. Predecessor. Sorry, predecessor. Successor or predecessor. That means instead of bringing the smallest bigger value from the root, from the right subtree, you bring the most bigger value from the left subtree, like this figure. You either bring, if we want to delete 25, you either
yes. You
bring
print
35.
35.
Yeah, you either bring 35 as you answered from few seconds, or we use the predecessor, which means the most bigger value from the left subtree. Here it's 20, so you bring 20 and put it instead of 25. Or from this example, like here we are deleting 20, okay? So we go now, if we want not to use successor, predecessor, so we go to the left and see which one is the biggest one is the 19, correct?
Yes,
So we bring the 19 to here and delete the original place. So 19 will be the place in the place of instead of 20. So you have two options. It's up to you to use whatever you want. But let's use in this course the successor.
yes,
Yeah, but it's just like mentioning that you have two terms, the predecessor and successor, and you may use one of them, and the BST will still a correct BST. I mean, we're still preserving the condition of the BST.
yes,
Okay, okay, okay. So the code of delete node. Um, Let me see. Okay. Uh, we have like we have now, as we have more cases, we need to add more conditions. It's not as simple as the insert. So first of all, if the usual thing, if it's and here, by the way, we are not we are using recursive and with extra conditions. So you will see here conditions and recursive. So first simple thing, if root is equal to null, that means if it's
return.
empty, or you reach to the place that it has no children, So you simply return root, and we will see why you will return root. Now, when we want to delete, we need to reach to the node. I mean, you pass to the function only the value you want to delete. So you are not pointing to the key itself.
Yes.
Okay, let's go back to like an example. Let's say we want to delete, just for simplicity, 29. So currently you are passing the tree, or the root of the tree is 72. So currently you are not at 29. So the first step is to reach to 29. So this is what's happening here. You check, is the key is smaller, again, like insert, is it smaller or bigger? If it's smaller, that means you need to go to
Left.
left. So again, you do the recursive by calling the left of the current node and passing the same key. If it's not, it's bigger, so you go to
Then right.
the right, exactly. Now, the else means it's equal to the key. That means you reached the key you want. Insert, you don't need to add a new condition to say the key you want to insert equal to the key of the node, because you are inserting, not deleting. You are not searching for a certain key. But here else means that the key you are trying to delete is equal to the node you are currently in it. That means you reached, let's say we want to delete 29, that means you reached to 29. Okay, unless than that, you are still calling the delete node. Now, when you reach to the node itself, now you start like the complete code afterward is related to the else, this else. Let's move this code. Sorry, let's move this code to like an editor so it will be more clear. Sorry. Let's use Notepad. So again, like if you see here, the complete code afterward is and here else. Let us put it as C++ just to make the syntax highlight. Okay. So else here we are talking about is reaching to the node to delete.
Yes.
Okay. Okay. So whenever you reach to the node you want to delete, now you need to discuss the condition you are facing. Again, you may have different scenarios, you may delete a leaf node like 20, or you may delete an internal node, or you may
or root.
or a root. I mean internal node that has only one branch, not two branches, or you delete a node with two branches like root, or another internal node that has two branches like 70. So here we discuss one by one. Here it says if left and right equal to null, that means, what do you think?
And there's not no children.
Yeah, that means it's a leaf.
Yes.
So you are going to just now it will return null just to break the recursive, but you will see that you will simply delete the node and update the link with the parent. You will see it now. It's just expressing each condition. What is it? Now
If the left is null, then we delete the right. Is it?
Sorry, no. If the left is empty, that means yeah, exactly. You will delete the
Yes,
right. Yeah.
yes, right.
No, wait, no. If left now, we are saying that we reach to 30. If left if left is empty, like here, like 30, if left is empty, that means you replace the right with the current node.
Oh, we delete 30. Yes.
Yeah, so replace with right branch, and here obviously will be replace with left
With
branch.
left branch.
And that's why temp now here temp you is mention is like pointing to the root here now in this recursive iteration. It's the node we want to delete, and only has one hand or one connection, which is right. So we assign the right of the node we want to delete to the temp, and then delete the root, which is the node we want to delete. We are currently we are currently in it, like here. Let's say at or not here. Let's say, sorry, like here at 30. We are deleting 30. So you are currently at 30. So you are going, first of all, before deleting 30, if you deleted 30, you will delete 30 and the connection, right?
Yes.
Yeah, so first of all, you need to store the connection at a temporary variable, then delete 30. So this is what's happening here. You first store at a temporary variable, and then delete free or delete, it's up to you, delete or free the root, which is the node uh, you want to delete, and then return temp. Now returning temp, you will see now returning temp is only for updating, because 30 has a parent, right, which is 50. So you need tell
Yes.
50 that you have now a new address, which is the address of 40. Okay, so you
Yeah.
can
Okay.
make this connection. So here is the same thing happening here, will happen here, but with the opposite branch. Okay, like
Okay.
in just instead of replacing the right, you are replacing the left. Now we are discussing now if none of these conditions happened, it's not a leaf, it's not a node with one branch, either right or left. That means you reach to the case that uh, the node you want to delete has two branches. Okay,
Yeah. Okay.
two branches means we need to go and get the successor. Okay,
Okay.
starting from the node that we reach to and the node we want to delete. I mean, like if we want to delete the 70, starting from the 70, we search for the successor. So here, like this function will go and get for you the minimum value. We already have a function, I think from the slides you already have a function returning for you the minimum value, and I think we got it from the even from the lab sessions. uh, I think we already solved it, getting the minimum value for the right branch of the root, the right branch of the root we want, or the node we want to delete. Okay,
Okay.
now we just updating we are updating the key of the current node before deleting it. We update the key with the key of the successor we search for. For example, now when we delete here 50, so we update the node here, the key of this node with the key of successor, which is the 60. Okay.
Okay.
And now you should update the right. Let me check. Yeah, now this you know this one this recursive, you will still recursive with the delete node until you reach to the end of not the end, you reach to the because let me express in another way. By doing so, until now you did not delete anything, right?
Yes, we didn't delete it.
Yeah, so you still need to do recursive until you reach to the node you want to replace, because the successor, I mean, until you reach to the successor and delete the successor. You see here, like, look here, here instead, like in delete where here in delete node here and here in line 7 and line 11, we are calling delete node with what? With the key, this one.
Key, and we point to the temp.
Yeah, but here, if you see, like you are calling for the key of temp, that means the same thing you did for the normal case of deleting a normal node. If you are in case 1 or 2, you will do it, but not for the node you want to delete. It will be now for the successor, because the successor now is replacing the root. For example, here, like 50, 60, which is here, is replacing the 50. We already saw this from here, right?
Yes.
So this line 33 means you are updating the key of the node you want to delete with the key of the successor, which is the temp, and temp is the successor, which is we got it from the mean value node. Okay.
Okay.
So now we finished replacing only the value of the key with the key of the successor, but the successor itself, which is like here 60, it's still in the tree. So if you printed the tree, you will have 60 here and 60 here. Okay.
Okay.
To solve this, we just now saying to the tree that now you need to do the same thing, but this time not for the key, because the key you already updated the node with the key. Yes. But now just delete for us the successor. Okay.
Okay.
Okay. So this is the code of deletion. Is it clear, or you want me to repeat the explanation?
No, clear.
Look, this code is not simple to understand.
It's not.
But I think if you go back, go back, because you are in the cafe. When you go back to home and watch the recording again, or trying to go line by line like what we did already, you will understand it easily.
I understand better when I did practice on my own.
Yeah. But the most important thing to understand that the complete code is just like we are, except this line. The complete code is just expressing the cases we already saw. I mean, like here, just to make it easy for you. This part we are just searching for the key. We are just here. This part means that we are searching for the key. We are waiting until we reach and pointing to the key, because we start with the root and now we are traversing through the tree until we reach to the key or to the node we want to delete. So this is the first part. And again, as I told you, this else completely executing after we reached to the node we want to delete. This else.
Yes.
Inside it, we have three conditions. First conditions discussing the case number 1, which is deleting a leaf. Case number 2, and sorry, these are 4 conditions. The case number 2 and the 3, which are the same, discussing case 2, which is deleting a node with one connection, either from right or left. This will include what? First of all, storing the children, the only children of the node we want to delete in the temporary place, and then delete the node, and then update the connection. Updating the connection will be from the recursive, because the recursive here from here, like you need also to understand that this is not recursion. Again, we have like entry in the stack, so you need to understand that the right or left will be updated correctly after deleting, because here true you are deleting the node, and you are returning the address of the temp, which is 40, and by doing the recursive
we are swapping them.
Yeah, in backward, you are going to update one of these. You are updating one of these until you have like the correct tree. Okay.
Okay.
Now we discussed again these 2 conditions. The last condition is now the case number 3, that the node has 2 connections. And now you simply want to find the successor. Okay.
Yes.
The successor will be the key of the successor will be replacing the value of the node you want to delete. And finally, you want to delete the successor. This is just the like strange line here. Like you finished everything and you want to repeat the whole thing, but this time not to delete the key, to delete the successor. Okay? Okay. Let's have a break, 5 minutes, so or 4 minutes. And let's meet at 5. We don't have too much thing. We only want to discuss the next part of the Labo project. Okay.
Okay.
Okay. So from where we okay, here. Now I just want like 10 minutes, and when we finished, also like small exercise also, you just need after doing exercise 1 or using just the deletion, you can like use the deletion, this code. You use the same class here.
Yes.
So you have the same class, the same class PST. You just bring the deletion or delete method and use it inside the tree. Okay. Inside the PST, and then show me an example usage for it. First of all, you insert. So if you want to use insert, you need to have the complete PST. You have the traversing, the insertion, deletion, and And then you do the example in the int main. You just insert and then delete and then print, just to make sure that the code went correctly. Here, like, you try to print, try to delete the root and check. Okay.
Okay.
And also you can use the same website already saw if you want to visualize how this deletion works. You can also try, like, here, let's 72, you can delete it, so it will show you step by step. Like, here it's simple because the right branch is only few nodes, but if it's let's choose to delete the 54, so to go to get successor from the right. So again, the same thing. This is the successor, delete it and replace it. Okay.
Oh, yes, okay.
Okay. Now let's discuss the lab project. This is the same, like the same requirement.
Yes.
I'm assuming, I hope we did not have this misunderstanding. I assume that you already was able to read the CSV file, or you remember I explained to you the dataset we are going to use for
Yes.
good readers. So I assume that you already now able to just get the file, read the content, specifically the author's name and book titles. And now, today we are going to discuss or give you some hints how do you can finish the next part. The week after, we will discuss the third part. By doing so, I think let me check. Next week it will be 3. Then it's the mid quiz, or not mid quiz,
Yes.
the quiz, and then the final. So you have, if you could finish in next week, if the first part, and by 10 finish the next part, at 17 you could complete the project.
Okay.
Okay, so this week we will discuss fetch a list of all books that start with a query string. Like, you fetch all the books with starting with a name as an introduction. To fetch all books start with this string. By the way, I may simplify the request and just asking you to search for the complete name of the book. So instead of like fetching all the books that start with the substring and introduction, I may ask you just to search for the complete name of the book. So an introduction to mathematics, for example. Because I think it will be a little bit difficult to implement this, or you may not have too much time to do it. So if we had time, it will be a substring like an introduction, and you bring all books with start with an introduction. But if we did not have time, you simply search for the complete title. So how you are going to solve this? I mean, let's imagine you finished this part. You already have extracted from the data set. You extracted the book titles. You already have the book titles. How you are going to build the BST? Because book titles are strings, and last week you asked me how we are going to build a binary search tree, but this time not for numbers, it will be for string, right?
Yes, strings.
Yeah. So first of all, you need to know that we have a term called a lexicographical order. This term is identical to dictionary. How you use dictionary? I mean, you have order of words. So, for example, apple has, or let's say able as a verb is become before apple, because both start with A, but P for apple is in the alphabet, English alphabet, is after the B of able, right?
Yes.
Yeah. So this ordering the words according to the chars inside, or the alphabetical order. Let's say you can say simply it's an alphabetical order. So this called lexicographical order. This means the order. So starting from this fact, we can may say that we will use this fact to build the BST. Okay. Again, so starting from this fact that we have an order for words, we can use this order as a number to decide which node should come to the left or to the right.
I got it. Okay.
Okay.
Yes.
So to help you out, I attached or put a code to not to calculate, to make the order. I mean, you have the list, like if we imagine we have the data set. The data set is not ordered alphabetically. Okay. So you need to do the order. At least first of all, you need to order the book titles, because the first book may start with B in the data set, in the CSV file, and the last book may start with A, for example, an introduction. So you need to order the book, because you have all the book titles and they are mixed, is not ordered. So to order the books, I attached for you an example. In C++, string is a class inside the std. So in this class, there is a method called sort. Sort exactly do the lexicographical order. Sorting, yeah. So, but using sort will be in a certain way. You first create a vector. If you remember, I like mentioned vector before. Vector is like you can imagine vector as an array. No need to understand exactly what is a vector, but you can understand vector as an array if we want to oversimplify vectors. Yeah, I mean, like, yes. Vector is like a data structure that you can store elements to it, like assign element to it. Like array, you can assign different element, and each element will have an index, right? Vector is the same, but different than the type of an array. It's another type. And what you will see here, like, you can use the code as it is. I mean, you can use it as a black box, but I'm just explaining just to be not like to be more clear to you. This place, let's move it to the notepad to be more large. Let's make it like this. Okay. So let's put it here. Yeah. So this is vector. Just vector is something internally in the C++, and again, it's like an array. This way is just, I also mentioned to you once, I mostly you forget it because it was like from our next session. Sorry, not our second session. This called a template in C++. Sometimes you want to have a class that may accept different types or different data types. So instead of having a class for each data type, you can use template. And template as a word is something like you have like a formal thing, and you can use it in different ways. So you have the vector as a template. You may have a vector of strings, or vector of integers, or vector of floats. It's something like when you create an array, you say int array and you specify the size, right?
Yes.
Or you say float, or you say char, whatever. Template give you the dynamic give you dynamic way to have one declaration or one class declaration, but inside your code you specify what the data type. So you can imagine it as an array that can take any data type you want, but you should specify during the run during your code what is the data will be. So this means like this vector will contains strings. Okay.
Okay.
So this vector of strings, you will use it to store the book titles. Here I just added like names with like mixed order, alphabetical mixed order, and then I tried sort, and here I'm just printing the names. Okay. So
Okay.
you will have here as an output the names ordered, not the names, the string array or the vector itself will be ordered. So if you want to access element by element, you will have it unordered. I mean, initially when you push Ellen, and then Tom, and then Wendy, when you want to access this vector, by the way, you can access the same way of array. So this is at index 0. Okay. This is at index 1.
And 2 and 3.
And so on, yeah.
Yeah,
and so on. But after calling the sort, the one with index 0 will not be ln, will be alan. Okay.
Okay.
So the complete it will sort and change the order for you. This part, no need to understand it. It's not required. It's out from the course. But this is the way you can iterate through the vector. There is a special way called iterator. No need to explain it to you. You can use it as it is. It's simply this line simply is you will start iterating from the beginning, just like I will direct your focus about this part. You will iterate from the beginning of this vector until the end. You remember, yeah, as like any formal or usual for, you start with something and end with something, right?
Yes.
The start will be the beginning of the vector, which means the ln, and the end
and John
will be the end of the vector will be John. Exactly.
Yes.
And
So
you
it's up
simply
to
start.
me.
Sorry?
The begin and end, it's up to me.
Yeah, it's not up to you. It's about the content of your vector. I mean, yeah.
Yes. Yes.
Yeah. So you can reuse this code, but instead of printing, you will have your own code, like building a binary search tree. Okay.
Okay.
Now we are moving to the other. Until now, you have like a straightforward way using the hints from last week. If you remember, I attached a code for you to read the CSV file. After reading the CSV file, you will have a list of book titles and author's name.
Yes.
And after that, you you like create a vector and push name by name. You may start simply only with the book titles. So you push book title by book title to the vector you have, and then you sort it. And when you have the sorted like the sorted vector, you can start with building the PST. Now there is that it's the time to discuss something else, which is how to build. Like usually when we build binary search tree, if you remember from 2 sessions, I think I gave to you an order of nodes, and we build the tree, draw the tree, right?
Yes.
Yeah. So you may have something. Let's go back to the one I am mentioning just to be more clear. Lab 6, I think. Okay, yeah, this one, like not this one, not this one. Okay, so it's here. Anyway, it's too slow, too slow. The idea I want to bring this idea to you, that usually we have mix order and you ask the build to build a tree, but this time after you order the book titles, you have no like mixed number. Let's say you have like first book, second book, third book, fourth book, fifth book, and so on. I mean what I mean, like the first title in your list, if we want to represent it as a number, what it should be, it's like the index of it. It will be only one, and then two, and then three, and then
Yes.
four. I mean the lexicographical uh, order is not represented by like a random value. Like the first book has a value of 100, and the next one have 100. Let's say 5, and so on. You may express it by its index, right? So you have first book,
Yes.
second book, third book, 5, 4, 6, 7, 8, 9, 10, for example. I'm just like writing a sequence for you just to make an example how to build such binary search tree. Let's say you have 20 book only. How
Yes.
you are going to build a binary such thing, such binary tree starting from this order?
The most, the smallest one is most left.
That's the point. If you build it from one, you will have like
Yes.
without a drawing, it will be like here it will be one, then two, then three, then four, then five. you have a tree only with left branches, right? There is no right.
Yes.
Or sorry, with right branches, not left branches, with right branches. Because
Yes.
one is the
It's bigger than
smallest.
one.
Yeah, so
Yes.
you will have a tree with 80, 19 branch, right?
Yes.
So
Yes.
he,
So with one
yeah,
root, it has to be nine left. Pardon. Sorry. Uh, eight left, eight right, and one root.
actually, even this one is not good because this is another thing I wanted to discuss with you before. Uh, like I forget to discuss with you. Let me bring like complete tree, binary tree. If I ask you a question, what is the most important thing for using tree for search when you want to search a data? Okay, let's say you have list of numbers. Okay,
Okay.
1 to 20. Let's say 1 to 20. If I give you only this list, okay, this is the question. Let's say I gave you this list and told you it's up to you to use whatever programming solution, but I want from you to search a certain number between these 20 numbers. Okay?
Okay.
What is the point of building a tree for these 20 number? What the benefit of building a binary search tree or binary tree for such numbers? Why you don't search one by one? Start from the first one until you reach uh, to the number you want or you search for. Actually, it is the main point of algorithms. In the first session, I give you, if you remember, the analogy of preparing tea. You need to
Yes.
find the best way of doing the job with the minimum effort and minimum time. So if you choose to search for the number by like checking one by one, okay, you may find
Okay.
the number very fast. If I give you like the same list, if I give you the same list and told you search me for one, how many execution will do? Only one. Because if you start with
Yes.
one, it will be equal to
Yes.
one and you will return an answer. But what if I told you search me for 20? You will go through all the whole list. You will go one
Yes.
by one. One is not equal to 20, two is not equal to 20, and so on. So you need to go through all the list.
Yes.
But instead, in the binary search tree, you will have a tree. Okay, you will have the tree organized so you can find any number in the worst case with how many iterations it will be equal uh, to the depth of your tree. Because
Yes.
imagine any tree you want, give me any tree you want, I can reach to any node like this tree. Let's say we have this tree. Okay, give me any
Okay.
nodes to search for. The worst case to search for or to reach to it is only three. Like if we want to reach L, we will have this movement and this movement and this movement.
One, two, three. Yes.
Yeah. If we want K, we have the same. If we want C, it will be one. But
Yes.
for
One.
the worst case, it will be only three. The same
Yes.
thing. The same thing for this list. This list. Instead of having 20 move or 20 iteration to reach to the correct answer, we
We
will
are
have,
dividing to left and right.
yeah, we have I think this tree will be enough to have three movements. So this is you should understand this. We are not studying just to know that there is something called a tree. You need to know that a tree is best used for such problems. So if you have search, if you use a binary search tree, you know that the worst case of binary search tree, it will be the height of your tree. So you can reach any node with only equal to the height of your tree. Okay?
Okay.
So, and by the way, this is the topic of the next
session.
semester. No, next semester.
Yes.
Yeah, the second part of this course will be discussing this exactly, the complexity of the solutions in algorithms, or the complexity of algorithms and data structures. So you will study exactly what benefits you are getting from using this data structure or this algorithm to solve certain problems. So you'll study and try to find and compare different solutions, and each solution, how much time complexity or execution complexity you have to do to execute the algorithm with your problem. So back to the to the project, you will have an ordered book titles. It will be ordered from 1 to 20. In my opinion, to build a tree, you can like start from the the root will be should be bigger than something, and smaller the things will on the left will be bigger, and the things on the left will be smaller, right?
Yes.
Yeah. So the most like logical thing to start with is 10, because 10 it's in the middle. So it has 10 numbers to the right and 10
Yes.
numbers to the left.
Left. Yes.
So if you start with 10, you can now have two groups now. You have this group, sorry. You have this group and you have this group. And now 10 is already taken. So you can repeat again. Start from
Yes.
the
We can
middle.
divide again.
Yeah, start
Yes.
from the
5.
middle, which is
5.
5,
Yes.
and 15.
Yes.
Okay, so you go here and put it 5, and you go here and put it 15. Okay, and this is taken, and this is taken.
Okay.
And you repeat again the
Then
same
again.
process. Yeah, but
Yes.
not you may not always have like how to
Yes.
say equal left numbers. You may use 2 or 3, for example. So you can let's say
3.
use 2, yeah, 2, and use now the right sub numbers, like from 6 to 9. You may use 8 or 7. So here
Yes.
you may use 8 or 7. And now 15, let's say you have now here 12.
12. Yes.
Let's say we will use 12.
Yes.
And here 18, let's say. We go back now. We have 1. Let's use 1. And then we use from the 8 we is already taken. We may use 6 or 7 and continue.
Yes.
Okay, so
Yes,
so
okay.
you end with this tree. You can now you have a BSTT. You have a binary search tree, but you only have now indexes inside it. Inside it, you can store indexes. You have now this is our vector, right?
Yes. So
Vector which contains the strings,
yes, strings.
and here are the indexes. So you simply, when you want to search for to search for a string, you simply start by compare. There is another function called compare. Okay, in the C++.
Okay.
This is we will discuss it on next week, I think. But it's just to give you a hint. You start with compare. You compare the string you have with this. Is it smaller or bigger? Because it will compare the lexicograph graph order. Is it bigger or smaller? If it's bigger, you go to right. If it's smaller, you go to left, and so on. It's like by doing so, you are like just solving a normal binary search tree. Okay.
Okay.
But what I want to say that from like a conclusion, if we want to like conclude what we already discussed for searching a number from this list, the same thing is for our project. What the purpose of our project? What is why we should be interested in this in such a project? We should understand what this
I
project
can
may have.
replace with one with A
So
letter. I can
sorry.
replace with one, most at one with A letter, A index.
Um, yeah. But I mean the complete. Yeah, I understand you. But I mean the complete idea why we are building a binary search tree for a database of books. The complete idea is to make search faster. So let's say if we stopped by building a vector that contains the book titles ordered, we will have the same problem. Let's say I told you to search for a certain book for me. This book may be in the last element of the vector or maybe in the first of the vector. But it has a worst case that you may scan all the book titles until you reach the book title I want, right?
Right, yes.
But in our problem, we don't have 20 element. We have 1,000. I think it was one or 2,000s. So it's a big list. In real world, you if you are like building for a real library, this library may have like the library of university may have like thousands of books. So your program will be slow. But instead, if you build a tree for the big book titles, the worst case will be according to the height of the tree. Okay?
Okay.
So I think that's all for this week. I hope it was clear for you. If you have any question, please ask me.
No, right now. I will
Okay.
make practice at home.
Yeah, okay. So again, it's for your own benefit. Try to solve at least for next week the first part. So you can complete the complete project. It's not hard, especially that I'm trying to give you too much hints. So it's just by practicing what I'm giving you as hints. You have the codes, and you just need to. It's like Lego. You just need to bring together the code blocks I'm giving to you and apply it for the project.
Okay.
Okay.
Thank you, Tor. Thank
Thank you.
you.
Thank you. Okay, so see you next week.
Merci, sir.
Okay, inshallah. Have a nice weekend
Have a
and
you too, sir.
goodbye.